Okay, we are live. So, hey everyone, and welcome to the Latin American webinars on physics. Today is a very special occasion for several reasons. First, because we have Gian Giudice as a guest speaker, and also because today is our webinar number 200. So, just a recap of the history in a minute. So, we started 11 years ago already. So, yes, in March 2015. So if you remember, for webinar number 50, we had John Ellis. For number 100, we had, was very special. So we had Ray Weiss and Kip Thorne, actually, two Nobel laureates. For the 150, we had Juan Maldacena. And now we're in crescendo. We have Jan. So it's a big pleasure to have him here with us. So Jan was the director of the theory department at CERN for 10 years. He was there for 33 years. And now we're super happy to have him at NYU Abu Dhabi. So Jan, so the dance floor is all yours.
Thank you very much. Let me first of all share my screen and go full screen. You see?
Yeah, perfect.
So thank you very much. It's really a great honor and pleasure to give the 200th Latin American webinar in physics. I want to thank especially my NYU colleague, Nicolas Bernal, for organizing this event and for the invitation. So from CERN to Abu Dhabi to Latin America, theoretical physicists belong to a single family. The theory community is an international and well-connected network of amazing individuals. And this is the aspect of our field that I love the most. In this series of seminars that involve a large community in South America is a wonderful expression of the international character of theoretical physics. And we should really not underestimate the importance of keeping our community united. Theoreticians have typically strong individualistic personalities, but at the same time, most of us value the sense of belonging to a single family that stretches across the planet. And in these times of war, of conflict, nationalism, this role of bridging across cultures couldn't be more important. Science should stubbornly maintain ties even between countries in war. We are not going to change the world, but we can show a model of human relationships based on mutual understanding, international collaboration, and the desire of always resolving conflicts and disagreement only with the force of reason. I know that I'm addressing this seminar to an audience preliminary of primarily of young researchers at the beginning of their scientific career. And I hope that all of you will uphold the principles and the values that have characterized our community in the past. Doing theoretical physics is not only about solving equations, but is also about pursuing an ideal of science free from any racial and cultural prejudices. And as you advance in your career, never lose sight of what are the values that define our community. And during my career, I had the privilege to work in institutions that value the principles of international cooperation, mutual understanding in the interest of science. So CERN is one of the best living examples of what international cooperation in the name of peace and science can do. And today, physicists from all over the world work at CERN and collaborate with CERN. And CERN has extensive collaboration with Latin America for fostering particle physics research in your continent through international cooperation with 12 countries. And moreover, Brazil became the first Latin American associate member state in 2024, and Chile followed last April, so very recently. And CERN, in collaboration with various Latin American institutions, organized successful biennial school series, one in high energy physics, the other one in computing. And the theory department, which I stayed for so long, has a fully international hiring policy. Many theorists, many colleagues from Latin America have spent periods of their career at CERN. So I encourage you to apply to CERN for jobs, research visits, participation to workshop. Really, CERN belongs to Latin America and to its theory community as well. And you will find there at CERN the true spirit of international collaboration. I had fabulous 33 years at CERN, but now I am in another amazing institution, which is New York University at Abu Dhabi. It's a true melting pot of cultures, and also at NYU you breathe an international atmosphere at its best. So throughout my career, I came to appreciate the value of being together as a community beyond any border. And this is the spirit that animates the Latin American webinar series that we are celebrating. So happy 200th birthday. And congratulations to the people who are behind this wonderful initiative. So let me now come to physics, although this is not a real seminar, unlike the 199 webinars that preceded me. It's just an occasion to celebrate the wonderful Latin American webinar, and I want to have just a conversation about particle physics. And I've chosen 3 topics of conversation out of the many interesting open questions that characterize today's landscape of theoretical physics. There are 3 topics that share a common theme that I will explain at the end. So let me start. Topic 1, gravity. Gravity is the most familiar force in our everyday experience, the first force that was tackled by physics, starting from Galileo, Kepler, Newton, and yet it remains one of the most mysterious. Certainly, general relativity has unveiled the fascinating connection between gravity and geometry, but we know that this cannot be the end of the story. And the problem is quantum mechanics. Quantum mechanics dictates that every field must break up into individual quantum excitations. And general relativity tells us that the gravitational field is defined by the metric of space-time, its geometry. And so if we put together the 2 things, we conclude that necessarily space-time must break up into individual quanta. In other words, space-time cannot be a continuum medium as we usually envisage it, but it must be made of some new purely quantum entities. We don't know what these entities are, but it's interesting that we know quite precisely the minimum distance below which the continuum description doesn't make sense. And just dimensional analysis, we know that this distance is the Planck length, 10 to the minus 35 meters. A distance which is so small that it's impossible to explore it with current experiment. For all we know, the classical description may break down much earlier than that, but we are sure that general relativity cannot be extrapolated beneath the Planck scale. Actually, there's nothing mysterious in this. Take the Einstein-Hilbert action that gives the general relativity equations of motion and quantize it in the familiar way. There's nothing wrong in the process, but the problem is that the quantum theory that you obtain violates unitarity at an energy scale of the order of the Planck scale. This signals that the theory makes no sense because it predicts probabilities larger than one. Again, also this is a very familiar phenomenon that we have encountered already in the Fermi theory of weak interactions or the nonlinear sigma model of electroweak interaction, the Higgsless model, if you wish. We know how to deal with these cases, and the answer is just increase the energy of your probe. And this is what led to the discovery of the W and the Z bosons in 1983, and the discovery of the Higgs boson in 2012. So the experiment identified the elements that unitarize the initial theory. So can we do the same thing for gravity? Well, the first problem is that you need a Planckian energy collider. So how big is that? Well, suppose that one day we could build some large scale dipole magnets of 30 Tesla using high temperature superconducting materials. Then to make collisions of Planckian energy, you need a ring that goes from here to nearly the center of our galaxy. So this would be a truly galactic high energy collider. I don't know if it will ever be built, but I know that this may not be enough. And the reason is a strange property of gravity. So we are used to think that high energy means short distances, because with high energies, you probe deeper into the inner structure of matter. But that's not the case for gravity, because once the scattering energy exceeds the Planck scale, you start forming black holes. And black holes has a Schwarzschild radius at a distance, it's a radius of 2e over m Planck square. E is the energy. And this horizon hides the inner region of space to any outside observer. And the bigger the energy, the bigger the Schwarzschild radius. And this means that as we increase the scattering energy beyond the Planck scale, we make bigger and bigger black holes, and we get less and less information about short distances, because an external observer cannot see the short distance behavior of the collision, which is hidden behind the horizon. And this is exactly the opposite of normal intuition. The higher energy, the shorter distances that you probe. So somehow gravity is special because it mixes infrared and ultraviolet physics. And this is a strange concept if you think in terms of effective theories. So building a high energy collider in the transplanckian energy range is a waste of money, okay, for a particle physicist at least, because the short distance are inevitably hidden under the screen of the event horizon. So we must pursue a different direction if we want to understand the short distance behavior of gravity. Black hole is a way. Black holes are amazing and fascinating objects from the general relativity point of view. The relatively recent observation of gravitational waves has really opened completely a new chapter in the exploration of black holes in action and also of the universe at large scales. They're not only fascinating objects for astronomy, but really they're a perfect playground for fundamental physics, for gravity in the strong regime, and for quantum gravity as well. So let's consider for a moment gravitational wave experiments from black hole merging. So as a particle physicist, I can visualize the phenomenon as a collider experiment. So I'm making two black holes and I make them collide. And in this sense, the experiment observed colliding objects of 10 to the 55 TeV. These are equal to 10 solar masses, but I am a particle physicist, so I wish to use my own units. And then they look at phenomena that happen 10 to the 25 meters away from us. So let's compare it to what happens at the LHC. At the LHC, we collide objects of 6.5 TeV, which is 10 to the minus 54 solar masses for astronomers, to explore phenomena that occur at distances of 10 to the minus 19 meters or less. So you see that we are talking about completely opposite regimes. So what do they have in common? And they have a lot in common, because in these two regimes, of the very small and the very large, nature exposes its simplicity. So these are the best territories to test fundamental physics and address questions about the fundamental laws that govern nature. Most of the range in between is dominated by complex phenomena which are beyond the interest of particle physics. But these two extremes are crucial, and both are very useful to improve our knowledge. So these are completely different tools, also experimentally, but these two fields of research address the same ultimate questions. You may say, oh, LIGO refers to astronomical observations that belong to the regime of complexity. After all, we believe that the observed black holes are microscopic stellar remnants. But on the contrary, black holes belong to the regime of the fundamental. Really, one can think of black holes as perfect elementary particles. So as Chandrasekhar said, black holes are, almost by definition, the most perfect objects there are in the universe. And this is summarized by the no-hair theorem, which tells us that for an external observer, the state of the black hole is completely determined by only three classical measurable physical quantities: so mass, angular momentum, and electric charge. That's it. There are no other distortions, no magnetic moments, dipoles, no nothing. No other structure or deformation is possible. And this is, in a sense, just like elementary particles. Take the electron, which is determined by its mass and its charge, its interaction. So let's compare for a moment a black hole with an electron. So because of its charge, we can assign a classical size to an electron, which corresponds to the radius for which the electrostatic Coulomb potential accounts for its mass. We can also assign a classical radius from gravitational interactions, equating the gravitational potential to mass, and we obtain the Schwarzschild radius. Now, for an electron, the Schwarzschild radius is ridiculously small. But notice the different dependence on mass. While the Schwarzschild radius grows with mass, the Coulomb radius gets smaller. So eventually, gravitational effects dominate, and this happens for masses larger than the Planck mass. So the Planck mass is large for collider standards, but it's small for astronomical standards because it's equal to 10 to the minus 5 grams. So it is difficult to satisfy the condition that Schwarzschild is larger than Coulomb in particle physics, but it's what happens in the case of astronomy. Now, these two radii, the Coulomb and Schwarzschild, do not correspond to a physical size of the objects in terms of some solid crust or something, but only defines a dynamical size in terms of interactions. And this is clear if you think of what happens when a point-like observer falls into a black hole. I said point-like because for an extended object, there are tidal forces that change the picture. But these are unimportant for our discussion. A point-like observer crossing the horizon would not feel anything special. Or more precisely, the observer cannot make any experiment to tell that the horizon has been crossed. However, that observer is doomed to fall towards the center of the black hole. And the same story would be for the Coulomb radius of an electron. But for an electron, the story is purely academic because of quantum effects. So the Compton size of an electron, which quantifies its quantum behavior, is bigger than the Coulomb radius. This means that quantum effects always dominate. And this is true not just for the special value of the electron mass, but for any mass relevant to particle physics. So the moral is that particle physics is a purely quantum science. In particle physics, there's just no room for classical physics. But gravity behaves differently from electromagnetism, because for a sufficiently large mass, classical gravitational effects win over quantum effects. And indeed, the Schwarzschild radius becomes larger than the Compton radius for masses larger than the Planck mass. So super Planckian black holes are essentially classical elementary particles. They are elementary particles, they look like elementary particles, but the difference from what we are used to is that those is a classical object instead of quantum. And so black holes are particles in which the classical horizon hides to an external observer the quantum behavior that necessarily occurs at the center, at the singularity. So a black hole is empty space up to a central core of Planckian size, where for a particle physics, all the interesting dynamics occurs. There is nothing at the horizon or the interior, because if it did, it would fall towards the center. And the story is analogous for the electron, which is a point-like particle from the quantum field theory point of view, but because of interaction, has a finite cross-section. So gravitational wave experiments are ultimately doing particle physics, but with particles that are too heavy for us to produce at a collider. And it all boils down to different units of measure. In the natural units of particle physics, the Planck mass is a small number. In astronomical units is a large number. But the story doesn't end here, because black holes are very special particles as they carry entropy. And although this idea that black holes carry entropy was inspired from classical considerations, the concept that black holes are thermodynamical systems is quantum, as is clear from the fact that the Hawking temperature vanishes as h bar goes to 0. And this quantum nature of the black hole degrees of freedom, is what provides the connection between black holes and particle physics. But the big surprise of the entropy of black hole is that it's proportional to the area of the horizon, not the volume. So this indicates that somehow the fundamental degrees of freedom are quantum and seem to live on a horizon surface, even if, as I said, classical, there's nothing at the horizon. And this concept is really powerful because it inspired the holographic interpretation that reality is just happens on the surface, embedding the volume, and the ADS CFT correspondence. So it turns out that the entropy of a black hole, according to Bekenstein bound, is the maximum possible entropy that you can fit in a given volume of size r cubed. And since according to the second principle of thermodynamics, the entropy of the system always increases, we can say that black holes are the ultimate state of matter. According to thermodynamics, everything should end up into a black hole. And using the formula, famous formula that is even engraved on Boltzmann's tombstone, very simple. Just put them inside a tiny black hole. It is really impressive that you can store petabytes of data in a device 1,000 billion times smaller than a proton. But it becomes a lot less impressive when I tell you that the device weighs a kilogram. After all, I can go to the store and buy a terabyte hard drive that weighs less than a kilo. So where is the catch? And the catch is entropy. So for ordinary atomic matter, entropy is an extensive quantity that grows with volume. While in a black hole, there is this unintuitive result that the entropy grows much slower. It grows with the surface. So by smashing a hard drive into a black hole, you gain in size, but not in mass. And it's easy to throw information into a black hole, but you just sinks into the hole. But how do you retrieve it? And the solution, again, is simple. Just use Hawking radiation. The black hole quantum computer is extremely fast. In only 10 to the minus 21 seconds, you get the processed information back in the form of high-frequency radiation that can be read with particle detectors. Okay, so I admit that there is some science fiction in this story, but with this story, I wanted to convey a message that black holes are strange and amazing objects, not only for astronomy, but especially for fundamental physics, particle physics, quantum gravity, and quantum information. Black holes really probe physics at the extreme boundaries of physics. And this is the goal of particle physics. They are extreme objects. They do not only extremize entropy, but they're also the fastest scramblers of information in nature because they satisfy the quantum chaos bound. And there is a revolution going on in this field linking gravity with information theory. And it's really exciting to follow this development and also to know that experimental data may end up playing a role. Subject number 2, artificial intelligence. So artificial intelligence is going to be, more precisely, is already a complete revolution for human society. It's able to perform tasks that were traditionally thought to pertain to the domain of creativity and to be distinctive of human intelligence, something that only humans can do, not a machine. But the boundaries of what we define intelligence and creativity are changing. Some of the tasks that AI can successfully perform are, let me just list them. One is games. Games actually have been one of the most common early applications of AI. And there's been many landmark events when AI programs won against grandmasters in chess or Go. And this hit the headlines of newspapers. That's how most people learned about the coming of AI. But then image recognition was also very important because computers were believed to be more efficient than humans in long mathematical calculations. But when it comes to pattern recognitions, human brains were thought to be superior. This is because pattern recognition requires inferring global properties of the system, not only local calculations. And recognizing global properties seemed a distinctive human ability. But now machine learning have already outperformed humans. So if you look in the old literature of AI, you'll see that the standard problem of image recognition was always to tell the difference between pictures of cats and dogs. If you're curious to know why cats and dogs were chosen, And the reason is very simple, that people like to post photos of their pet animals on the web. So there's plenty of data available online to train neural nets. Maybe our houses, there are lots of mosquitoes or cockroaches, but nobody posts their photos, only cats and dogs. Language. So another very important task is language, and task in language domains that were varied. There was to classify topics as inferred from a global context. Again, something very human. Translations into other languages, developing arguments, hold a conversation. And then there is science, and which is particular of interest for us. I mean, the most celebrated result is protein folding, which is a process in which amino acids combine in a protein and form a stable three-dimensional structure, which becomes biological active. And this has been a long-standing and fundamental problems in molecular biology. And then in 2020, the AI program AlphaFold, developed by DeepMind, scored a 90% success rate in predicting the molecular structure, which was an unprecedented result. By the way, when I was flying back from Abu Dhabi, I watched a fantastic documentary on this and really recommend it. It's especially for young people, I think is extremely inspiring. And anyway, it also has a happy ending because this result earned Demis Hassabis. He was a CEO of DeepMind, and founder of DeepMind, the 2024 Nobel Prize in Chemistry. But this is not the only result. There have been many successful applications in climate science, in data analysis, and in particular the LHC. Now, machine learning methods are routinely used, and many of my experimental colleagues are actively working on this. But despite all these successes, I think from our point of view, the point of view of particle theorists, the interest is not so much on what the AI can do for science, but rather what science can do for AI. Because indeed, AI is a science in itself. It poses many deep questions that can be relevant for physics and that can be addressed using physics language and physics tools. So one is, what is the AI thinking process? Okay, one can say it's a numerical optimization algorithm. This is it. But we may wonder, does it replicate our brain? Is it telling us something about our brain? Let me give you one example. It has been shown empirically in machine learning processes that after the training period, the machine is still failing for a while, long after overfitting the training data set. So it has all the elements to it, but in spite of having all the necessary information, the machine is still confused, doesn't get the right reply, and then all of a sudden, bang, it succeeds with a rate close to 100% with a delay. And this process is called grokking in their language. So learning for a machine is not an adiabatic process, but it's something that undergoes a sudden phase transition. Now, think about it. Isn't that what we experience very often as theoretical physicists? You know, you spend months studying a subject, reading papers that you hardly understand, you're confused, and you try many directions that lead to blind alleys. And even if you have all the elements in front of you to, in a sense, to understand, to solve the problems, you're still confused. And then all of a sudden, bang, you have this moment of eureka. So, and then everything is clear and understood. Why does it happen to both us and the machine? Are we grokking too? So understanding what is understanding for a machine is a very interesting issue. And let me make another familiar example. So take the standard model. For us, we say we do understand the standard model, because understanding is not that means that we are able to do every single calculation, compute every scattering matrix element, including all loops, level diagrams, or non-perturbative physics. No, this is not what we call understanding. Understanding for us is different. Understanding, for instance, the standard model means understanding the existence of some underlying principle. Once we identify the principle, we say we are understood. For in the case of the standard model, for instance, gauge symmetry. We understand gauge symmetry, how it works, and then we say, okay, we have the key of the solution. And then everything follows from that. Once we know that there is some principle, say a symmetry principle or others behind the theory, then we are comfortable in saying that now we understand the standard model. Is this how AI works? I really doubt that. AI is after solving a problem, not understanding the principles of the real world. So for AI, the point is that data is the only real world. So for AI, understanding means being able to map this virtual reality of data into a certain classification. And this is interesting for physics because it may lead us to redefine also our meaning of understanding reality and maybe our goals in investigating the physical world. And looking at problems with a different perspective often leads to interesting surprises. So fundamental physics is well suited to study AI because, as I said, AI is essentially a numerical optimization problem. However, this is done in a multi-dimensional space where multi is really some huge number. So it's a very tough problem because it's not simply minimizing a quadratic polynomial. But the logic is similar, and this minimization has to be performed in a multivariable landscape with a complex shape and behavior, something that is reminds you of the multiverse. And these are problems that we are regularly facing in physics, and statistical mechanics is really the language that is used to address this problem. And so it should be the language also to with which we can frame the complexity of machine learning with all these properties of chaotic behavior, of phase transitions, emergent phenomena, which are characteristics of machine learning and of statistical physics. So our physics language seems the right tool to unravel the process of machine learning. So there is much to learn about AI from a physics perspective. When science, when science fiction tries to invent the future, authors usually focus on transportation. So traveling around the galaxies, going at speeds with warp drives, energies, and engines powered by antimatter, spaceships that bring humans to other planets, cities with heavy traffic of flying vehicles everywhere. So this is the future, often according to science fiction, both in books and movies. But if you look back, humanity, after all, made limited progress in transportation. Cars and trains of 50 or 100, even 100 years ago are not that different from today, conceptually. The real revolution, the one that caused irreversible changes in the way we live, which is rarely predicted by by science fiction came from information technologies, not transportation. Each revolution in information technology deeply affected both society and science, bringing good things, but also dangers and fears in many of us. The first example in this side is the invention of writing. Information technology, the first information technology. Because according to Plato, to what Plato wrote in the Phaedrus, Socrates, who was his teacher, disliked and criticized the use of writing. Because, one, it weakens memory. Because not exercising memory, we become forgetful. Two, it encourages shallow understanding, because writing allows people to get a superficial overview of the subject. Think of when you use Wikipedia, right? You just you get the idea, instead of thinking deeply about a subject. Three, it creates passive learners, because for Socrates, the oral dialogue was crucial, and reading does not allow an interactive way of learning. Socrates' arguments are absolutely correct, but the conclusion is not. Reading and writing are not so bad after all, but they must be used in the right way. Without them, not much progress could have ever happened during civilization. Instead, Socrates refused to use writing and did not leave any text for posterity. Ironically, we know about his existence and his thought only because Plato and his other students wrote about him. So the use of computers and the web have changed the way we live. In many respects, is a positive way. The most obvious example of a positive way are the Latin American webinar series, because they couldn't exist without them. But Socrates' lessons shouldn't be ignored. There is some truth in it, and we cannot ignore the potential risks of new information technology, and this is certainly true for AI. There is a high level of risk, and that has to be regulated and not underestimated, but that doesn't mean that we should ban it. Should we be, this is a different question, should we be worried that AI will replace theoretical physicists, make them obsolete and irrelevant? Now, this worry may sound excessive, but I can tell you that I was present in conversations in which high-level academic administrators were seriously claiming that we should stop funding theoretical physics because AI will soon be able to do a better job than theoretical physicists. Now, it is certainly true that AI will change the job market. For instance, if I were a translator, I would start becoming worried, okay? Human translator will still be needed, but certainly a lot fewer than we have now. But for physics, it's different. The way we do theoretical physics will change. But theoretical physicists will still be needed, and not fewer of them. Physics is more than solving a problem or winning a computer game. AI is an amazing tool, but it's a tool. It's not black magic. Computation has always been a central component of theoretical physics. And every revolution in computation was followed by a revolution in theoretical physics. And here I'm not referring to the fact that with new computing tools, we can make certain calculations faster. That's trivial. But I'm saying that new computing tools have opened new avenues of exploration and thought, and allowed to attack questions that were unthinkable in the past. So as an example, think of the recent progress in lattice gauge theory. So I'm sure that the AI revolution will transform theoretical physics. But this doesn't mean that we will no longer use pen and paper to think. But we may be able to think with a different perspective. And this is true even for conceptual questions. Understanding the AI way of understanding could open a new concept of a scientific method, new branches of mathematics, for instance, or pose some physics questions that we have never considered before. So indeed, the power of AI is that you train AI for one task, and then AI will be able to perform a different task. Finally, a less exciting aspect of AI that we will have to face, or actually we are facing already, are new ethical issues in our field. Where is the red line between the ethical and the unethical in the use of AI for research? I mean, we probably all agree that it's fine to use AI as a tool to improve your English in the publication, or look for bibliographical resources for certain calculations. After all, we use Mathematica to do calculations, but we don't acknowledge in our paper, we don't feel guilty about it. So why should we acknowledge ChatGPT, Claude in our next paper? But now the point is very different. Suppose that the subject of the paper, the idea, the problem itself is machine generated. So who is the author in this case? The physicist or the machine? As an example, recently Matt Schwartz published a physics paper, just as a standard QCD result, and he quoted Claude as research assistant. And he wrote in the abstract, all calculations, numerical analysis, and manuscript preparations were performed by Claude, an AI assistant developed by Anthropic working under physicist supervision. So is this going to be the future? Well, Schwartz's experiment is interesting. Unfortunately, other authors are making a fraudulent use of AI already. And this is causing, for instance, a huge problem in scientific publishing, because physics journals are inundated by mediocre papers, which are most likely generated by AI. You read and you recognize it, but how can you prove it? Can you reject a paper because you feel that is AI generated? So there will be many issues that we'll have to face. And just one extra comment about AI with a cautionary remark. As I said, I'm fully convinced that AI will be the next revolution in knowledge. But I hear colleagues telling me that if you don't include the word AI or quantum in your grant proposal, you have no hopes to get it approved. So every academic institution around the world, large or small, feels always compelled to open new groups in AI. So my question is, will those groups produce valuable research in a highly competitive sector, which is dominated by private companies that have financial and human resources unthinkable for small and large universities? So I'm really questioning whether it's good for any small university to jump at all costs on the AI bandwagon, running the risk of abandoning other traditional activities that were established to be successful in the place. Let me get to the third topic. May I ask you how much time do I have? I'm afraid I went slower than expected.
Well, it's already 50 minutes, but
Sorry?
yeah, please. Already 50 minutes. Yes, 50.
Okay.
But please go.
50 minutes.
Yes, we just started already 50 minutes ago. Yeah.
Okay, so how much time do I have?
Say 10, right?
10. Okay, good. Okay, let me try then to go a little bit fast here. This is the topic closest to my heart, but I go quickly. This is high energy colliders. So the LHC has radically transformed our view of the particle world. What happened? As completely, redone an exploration of the standard model at a level which was unheard, with lots of new results. And this exploration will continue with a high luminosity, reaching precisions which are unprecedented. The Higgs physics, I mean, it's really impressive that in just a little more than a decade since its discovery, we went from the discovery, so unknown particles, to precision measurements. So now we know the mass of the Higgs of the per mil precision, which is better than the neutron lifetime, for instance. And it's impressive when you make these plots that directly test the Higgs mechanism, because they measure the Higgs coupling as a function of mass, and they perfectly are in a straight line with high accuracy. The precisions are already below the 10%, and they're marching on towards the percent, which will be reached at the high luminosity phase. The third and very important message is that there were no signals of new physics beyond the standard model. And this has completely made us to rethink of the process. In the summer, the LHC will end its phase of run 3. And then after 3 years of shutdown, it will go into the high luminosity phase that will last until 2041. So what do we need next after the LHC? We have some big mysteries open. You just stare at the standard model Lagrangians and you see immediately what the problems are. These are not in the gauge sector, which is well understood in terms of symmetry, but when it comes to the Higgs sector, so all the interactions that involve the Higgs, each one is causing problems. You don't know what causes the flavor puzzles, the pattern of masses of quarks and leptons, stability of the potential, the nature of this problem, and so on. Today, yes, we've done very precise measurements, but still we lack a true fundamental understanding of what is the mechanism that breaks electroweak symmetry. In a sense, it looks like a parameterization, just like the Landau-Ginzburg for superconductivity before you develop BCS theory. The Higgs boson will, the search will really start addressing many fundamental questions related to particle physics and to cosmology. This is really a not to be missed experimental program. If you say, okay, what do I learn especially? I mean, you can do many examples. Here I'm showing one example that you are testing the compositeness scale of the Higgs at the level of 100 TeV. So we are really going extremely deep. And this is very important because you can make a comparison to see what does this mean. And you can define a degree of compositeness as a ratio between the effective size of a particle and the Compton wavelength. And you see that for the Higgs at the moment, we have a precision which is less than the one of the pion. So the Higgs, for all we know, could be as composite as a pion, and we wouldn't be able to tell. And this is the goal for the future. Indeed, the Higgs has been identified as one of the priority by the European strategy. The second issue related with the Higgs is the mystery of flavors, of what is the origin of the masses of the quarks and leptons that you observe, and of their mixing. Now, for what concerns CERN, and I would say the international, at least the European physics community, high energy physics community? The answer is the FCC. It will be the next generation collider after the LHC. Is a 91-kilometer tunnel with a program that has two phases. One phase with the E plus, E minus, with 4 levels of energies, probing the Higgs and electroweak measurements at an unprecedented way. And then a second stage in which there is exploration at the high energy domain with proton-proton collisions that could go up to 100 TeV. The timeline is this one. At the moment, the plan is to have a decision, a final decision from CERN Council by 2028. I think it's very important that this deadline is respected, because the community is waiting, and it's very important, especially for young people, to know what the future is, whatever it is. And then the construction should start around 2030. As I told you, in 2041, high luminosity will end, and the operation of the E plus, E minus should start in 2045. So this is only a 4-year gap. It's, again, this is also very important, not to leave huge gaps that cover a generation of physicists between physics data of different machines. And at the moment, this is satisfied. And the idea is that the operation then for the Hadron version will start in the 70s and go on until the end of the century. The FCC is at a very mature level. There's been a feasibility study that has studied all possible consequences of this, really also going from aspects. Cost, of course, is the first thing that everybody quotes. The cost of the first phase is about 15 billion, which sound like a huge number, but you have to remember that this is spread in decades and decades, involving generations of physicists. And indeed, the current study of the funding scheme at CERN shows that the program is really sustainable, going beyond budget only above a 1.5%. We are talking about levels which are at the order of inflation. Recently, there was the new update of the European strategy, which stated clearly that the FCC should be the future of our field, with the possibility, the community was expected to propose a plan A and plan B, and the plan A and plan B are identical. The only difference is that plan B, if plan A is rejected because of cost, there is a possibility of a descoped machine in which costs are less, and but with a physics performance which is still reasonable. So let me now conclude. I want to conclude, and with this stream of consciousness conversation, I've touched 3 subjects: gravity, artificial intelligence, colliders. Gravitational waves have really been a game changer for our exploration of gravity, opening the door to new observational probes. And the science of AI is a mixture between computation, information, physics, theoretical thinking, making this subject so rich and full of promises. And the FCC offers the playground for unprecedented exploration on the nature of the Higgs boson and the physics in the multi-TeV domain. So these 3 subjects are very different. They seem completely far apart. But their common denominator is that there are 3 different examples of emergent approaches to fundamental physics. And so particle physics is in this very special situation. It is dominated by uncertainties and changes, and I don't know what the future of particle physics will be, but I'm thrilled to see that the field is broadening, and boiling with new ideas, building new bridges towards other areas of scientific knowledge. These are good symptoms that particle physics is entering a new phase of transformation that will only make our field more challenging and exciting. So thank you, gracias, obrigado.
Confusing.
Thank you very much, Jan. It was fantastic seminar.
Sorry for going a little bit over
Okay.
time. My clock,
So
I
it's a
don't think you
different-
heard it, was urging me to stop.
No problem at all. So, do you have questions or comments? Well, I can see one in YouTube from Chantal Desai. So the question is about non-zero neutrino masses. So this person wants you to comment about yeah, I think it's basically the future of a neutrino, non-zero neutrino mass in the in BSM models.
I did
And
not.
Stefan does not know.
Sorry? Should I
No,
read?
sorry. Yeah.
I did not mean to be exhaustive in the big open problems in physics. I totally agree that neutrino masses is still a very interesting avenue. It points towards new kind of interactions. It points towards new physics. And because of that, it is very exciting. It can probe distances, energy scales, which are unthinkable for colliders. It's fantastic. It's certainly one of the avenues. It's not the only one. I didn't mention about cosmological constant, about inflation, about, there's a list of problems that we have in our mind. They're all fundamentals. The choice was completely at random. All I wanted to say some topics which I find it exciting, and they link our physics to other things. It don't only repeat our own activity over and over, but it forms bridges towards neighboring field. And that I find it exciting. Particle physics, more than ever, needs to open its doors towards the outside, towards new ideas. And in order to do that, you cannot just simply repeat the same argument and continue with the same problems, but look around. Maybe some of the problems, we are dealing with fundamental problems, but trying to look for solutions that are borrowed from other fields, looking around. And that was my moral. This is why I didn't mention neutrinos, but I did not mean to diminish the importance of that question.
Perfect, thanks. Do you have other questions maybe from the audience now? Roberto?
Yes, I have a question. Very nice the talk, Jan. I wanted to, if you can comment, because you presented some point when you were talking about AI and the use of AI like a tool, for a physicist that is already formed to use AI to improve to connect ideas or something like that. But what do you think about the case of in which AI at the same time disconnect physicists or younger physicists because they trust more on the learning from the AI than talking with their advisor or the other colleagues or the other students of if they are PhD students? If you have some comment about that.
Yes, Socrates would not agree more with you, okay? Was exactly the point that was done at that time. He referred to writing, but I think the same thing, it will change, and every time there is a transformation, there are dangers. And I agree with you that, when he was talking about, Socrates was talking about shallowness of knowledge. This is exactly what you're referring. Not making the effort, we see, right? We're not making the effort of trying to think of the question. It's just faster to type it and get the answer. Will that be, we will reach the point that we will lack learning? We have to be careful. This is a big, important question for educators, for instance, the universities. How much can we allow? And at CERN, I was not exposed to this problem, and now at NYU, I've started to be exposed on this, and people at NYU are seriously thinking. They do not want to forbid students the use because they understand the value, but to try to define it. Homework, are they allowed to use it? And the rule at the moment, for instance, the university where I'm staying, it says, yes, they're allowed, but they have to declare it. They have to declare every time the way they used it. which is, I think, is a good way. It's not necessarily a solution because still, as you were saying, how about the knowledge that you acquire? Maybe one issue is passing the exam, the other one is really coming out of university with a solid knowledge and independence of thought. Are we suffocating the independence of thought? There is a danger, and the educators have to face it. This is why I'm saying that, like it or not, AI will be a revolution in our society because all fields will be involved. I mean, the job market is obvious, but education, schools, and high schools, how you do it. And I certainly do not have the answer. I'm not an expert in AI. I'm not an expert in education. But I see the problem as much as you do, and I see the dangers. It's going to be up to us when we deal with young people to try to instill the joy of your grokky moment and not just waiting for the machine to have the grokky moment.
Thank you.
And then the call will be quite empty.
I see another question. There's several, so I'm just read some of them. So Feforanda is asking.
I let you decide because I know that there's an issue of time also for people. So I let you do decide when it's time to maybe to stop. Of course, I'm available, for the future, online, messages, and for everybody.
Let me read one more. This person is asking if you can provide some general argument or idea of how can we trust the Schwarzschild radius when the energy is much higher than the Planck mass?
There are lots of people with a microphone on. Please turn it off because I hear many voices. I was a little bit confused. Could you just repeat the question? Sorry.
Yes, that noise is my wife. Sorry.
Oops.
So the question was about the energy much higher than the Planck mass. So when you discuss about the Schwarzschild radius.
Right. So this is a peculiarity of gravity. This peculiarity of gravity is that if you do a plot of distances, energy, you're always think that it should go like a straight line. The higher energy, the smaller distances, and so on. In gravity, it reverses. It takes over. So when you're probing higher energy, higher above the Planck mass, you're not testing shorter distances because you're forming a black hole. Now, in practice, this is not a problem because we don't have colliders that can probe that energy. However, conceptually it's very interesting. I can tell you that some years ago, with some of my collaborators, we were thinking about this, and we proposed the idea that this may happen not only in gravity, but it may be a more general property also for other kind of quantum field theories. If that is the case, really, I was mentioning the idea, what happens when you have a theory, you have an effective theory, which is not, which violates unitarity at high scales, and you know what the answer is. Oh, okay, I need to unitarize. I add some degrees of freedom, the appropriate degrees of freedom, that cancel the divergences, and now I'm getting a healthy theory. This has worked. I was giving examples, Fermi theory, electroweak, and so on. But what we were speculating, what if there are no other degrees of freedom? But what happens is something like for gravity, so that the theory cures itself, and the theory screens the short distances. So the unitarity is recovered simply because short distances do not take part in the process anymore. This is interesting from 2 points of view. One, what we're exploring, the idea that you could have other interactions of that kind. I must say that it was very speculative and the issue is still open. I don't think anybody has proved it one way or the other. And the second is gravity itself. Could that be? We always say, okay, gravity is non-renormalizable, which means that if I go to the Planck scale, there should be some new degrees of freedom beyond the standard model, say, or whatever quantum field theory you have to that scale, which they cure the divergences of quantum gravity, and then they bring into healthy theory. So we do expect, again, this idea that violation of unitarity must always be accompanied by new particles that do this job. There is also the speculation that you don't need it for gravity. When you go to very high energy, sort of gravity cures itself and makes it into a perfectly healthy theory. Your idea of these divergences is a mirage because you're extrapolating beyond where you can extrapolate using quantum field theory. Again, it's an open question, but all I want to say is that this different behavior of gravity, which is not interesting from the practical point of view, but it could have interesting consequences from a more conceptual point of view for us as theorists.
What to say, not to
Perfect,
say, right?
thank you.
It's not only
Maybe a very last question by Bastian. So he's wondering about the necessity of having the FCC take into account that there are some other experiments planned or around.
Sure. Of course, I strongly believe that the FCC cannot be a single answer to all the problems. Okay, so physics, particle physics, fundamental physics needs more than ever, because of this state of uncertainties we live in, needs a large landscape of different experiments. We need to attack our problems in different ways. This is why we need small experiments, low energy experiments. We need probes in astroparticle physics, in observational cosmologies. If we want to do progress, we need all these avenues. However, I also want to underline that high energy colliders are simply irreplaceable. For instance, suppose we didn't have the LHC. The question is, okay, but I do other experiments. How could you ever discover the Higgs boson? We don't know of any other technology able to prove the existence of the Higgs boson directly. And this is true also for exploration of at higher energies. So those kind of explorations are unique of high energy colliders. We don't know of any other tools, experimental tools that can do it. So if we give up high energy colliders in the names, but there are other experiments, we're simply going to miss a big window of opportunity that cannot be filled in any other way.
Great, thank you very much. So it's 15 past, so I think it's time to thank again Gian for this amazing seminar.
To talk today to Italy.
So, again, thank you very much, and we can.
Thank you all, and again, happy 200th birthday to all of you put together.
Thank you very much. So, the audience, we reconvene in 2 weeks with another webinar, and thanks again. Bye. Okay.